All right, so we're gonna go step by step on how to go from creating your main sketch to designing parts, and we're just gonna do this from scratch here. A few things that I wanna have open while I'm doing this is I'm going to have the folder setup that we talked about open for 3D print files, drawings, and part files, as well as my design calculator and part management system already open. I'm going to start in like a blank Onshape directory. So we're going to do this from like the very beginning. And then I'm going to have the field drawings open as well. So when I create that main sketch and I do my field elements, it's going to be in here. I'm also going to assume that I kind of know what my subsystems are going to be. So in the subsystems part of my part management system, like this is assuming that you've already done kind of like your brainstorming and your hand sketching with your team and figuring out kind of what types of architecture decisions you're going to have on your robot. So for C, I'm going to name that subsystem intake. And then for D, I'm going to be shooter. I think it's still at this point kind of to be determined if I'm going to do like a conveyor or an arm situation. I'm going to kind of decide it live to see how the shooter integrates with the intake. But these are all things that you should have kind of decided with your team before kind of starting this run. So first, I'm going to create my top level assembly. In this case, it's going to be in the Minibot design, my folder, and then I have a special folder that's just going to be for this filming. I'm going to create a new document, and it's going to be 24 TLA. 24 just being like the year that I'm creating this. And then I'm also going to rename it film so that when I search it in the search bar later, I'll know exactly which one this is going to be for. I'm going to create that document. And then first thing I'm going to do is, this is based off of what we did in class. So I'm going to bring in the drive sketch that we talked about earlier in class. Otherwise, you would have to create like a drive file as well, which we'll do eventually. But just to get the main sketch started, we'll go in other documents. You can go, I think for you it'll be shared with me, but for me I own the folder, so I'm going to go to owned UNLV 24. And this is actually going to be the tube and gusset structures. I'm going to look for the one that says drive, which is this guy. And then your drivetrain sketch is here, and we're going to start from here because this is where if you were designing your own drivetrain from scratch, you'd be able to pull up this type of sketch where it's just like a 2D side view of your drivetrain. So now that I have the drivetrain side view imported here, the next thing I'm going to do is I'm actually going to create my frame perimeter. I think when we talked about this in class, I did the bumpers first, which makes sense if you're doing something like a over the bumper intake over your drive. But I'm going to actually extend my frame perimeter to have kind of like a front section as well beyond the drive, to be kind of like my under the bumper intake style for this 2024 game. So what I'm going to do is I'm going to do a sketch on the top plane, and then I'm going to do a rectangle. And I know like this part of my wheel, that's the center of the drivetrain. So I'm going to create a center point rectangle, and I'm going to make these 2 points coincident so that they're touching each other. And then I am going to have this front point stuck to the front, and then this point, oh yeah, because it's center point, these two sides have to be equal to the center. So once I define one side, it'll define the other side. Next, I'm going to need to know what this side dimension is going to be. So just to do that right now, because I don't have it in memory, I'm going to go to that drivetrain file. And it should be, I believe, 24 inches if I remember correctly. But we're just going to verify looking at the drivetrain assembly. So if I click one of these lines that goes across the whole drivetrain, I should be able to see, okay, yeah, it's 24 inches sideways. So back in my file here, this is going to be 24. Okay, so this is my drivetrain perimeter as it is. And what I'm going to do is I'm going to add another construction line rectangle out in front. And I'm going to give it an overall dimension of, let's say like 31 inches. So if we're thinking about this as relating to the game rules, that means I have two sides of my drivetrain are 24 inches. So that's the front and back. And then two sides would be 31 inches. So that's 110. So I'm still pretty well under the frame perimeter limit, which would be 120. So that'll be the frame perimeter of my robot. And then what that'll allow me to do is I will do and this is frame perimeter. So usually when we do our sketches, we want to rename them so we can find out what they are later. Did I spell that right? I did spell that right. Okay. And then the next sketch, we're going to do the right side again. And this is going to be like the intake extension. So this will be the structure. I'm going to call it structure 2. This is going to be the structure that is going to define the intake position. So I'm going to assume this is going to be like some sort of 2x1 structure. It's going to go in line with the front of my frame perimeter. And as well, before I do that, I'm going to derive another thing that we had talked about earlier and actually I could do this in the first derived in context. Okay, so I showed you previously how to that we can mount one of these 2x1 with regular pattern holes on top of the drivetrain to give you a lot of mounting area on the side of your drivetrain, right? So we're assuming we have this and not this upper structure here. So I can bring that sketch into my TLA, my top level assembly. So let's say that I want to make this tube pretty much in line with this tube here. And then I know that this is also going to be a 2x1, so that side can equal the side of this tube. And then we want it to be in front of the drivetrain here. And then generally, I like to make these even numbers so that when I design the tubes themselves, they kind of always fall in equal increments. This gap here isn't going to really matter because what we're going to do is design a gusset that goes from here to here. Span this whole kind of gap area so that this bar can be held by this tube over here. So that's going to be my intake extension structure. And now I can do my bumpers on the right plane. Rename bumper. And then I can do my rectangle. And then I'm going to do construction line circle, tangent to each other, tangent to the wood, tangent to the wood, tangent to the top, tangent to the bottom, and then these two are equal. My wood is 3/4 of an inch thick, and it is 5 inches high. It went out there, and then I'm going to drag this closer to my structure here. I want this line to be incident to this line, and then because I'm going to try to get the note to go underneath the bumper, I want this to at least be like 2 1/4, which for reference, this means that this whole height is 7 1/4, which this turns gray because it's not defining the sketch, it's just a reference for me to see. But this is under the 7.5 inch bumper height limit in the rules. So this falls in line with the rules in terms of bumper height. Then I'm going to put the bumper on both sides. I'm going to create a construction line from the central wheel that goes up. And this is going to be my mirror line that I can actually, no, that's not going to work. It's going to be another construction line that goes from the very back of the robot to the very front of the robot. So this is the entire length from the back of the drivetrain to the front of the bumper structure. And then I'm going to look for the midpoint. It's going to show me a square. That's the midpoint. So that's actually going to be my mirror line for my bumper. So I'm going to touch the center line first and then copy the bumper, and then it's going to mirror to the other side. So these are where my bumper endpoints are going to be. Next, we're going to do some of our game constraints. So still on the right plane, I'm going to do a rectangle. I'm going to go right above that kind of bumper center mark here. And then I'm going to make my square or my rectangle kind of large. First thing I want is I want to make sure that this is tangent to the wheel. So that's going to mark my floor. So the center wheel is lower than the front and back wheel. So there's going to be a little bit gap here. So you want to do that tangent to the center wheel. And then this is going to mark my frame perimeter and the height that I want to try to hit. So for the coincident constraint, I'm going to go behind the bumper. So that's going to mark kind of the end of my frame. And then for the height, I'm going to specify 28 inches because that is the height for the stage area. So if I can design my robot to be inside this area here while it's driving around, that means that I'm going to be able to drive underneath the stage structure. Next, I'm going to do another construction rectangle still above that center point. This is also going to be incident to that same floor line, but I'm going to create a 12-inch buffer from the front of the robot perimeter to the outside box, and this is going to define my horizontal mechanism distance. So I can't extend outside of this outer box or else my mechanism will be out of line with the game rules. Same thing for the height. I'm going to do 48 inches because that's based on the rules, max height of the robot in any configuration. So as I design my robot, if any part of it in its range of motion extends outside of this outer box, it is no longer legal design. So that's going to be size box. So size box of my robot. Once I have my size box and my drivetrain in there, next is going to be the game elements. So first thing I'm going to do is I'm actually going to do the speaker as one of the primary scoring features of the robot or the game. And we see that there's this structure that lies 36.37 inches in front of the speaker. The speaker opening is 78.13 inches tall. And then the top of this kind of awning section is 82.9 inches tall. And that has a forward projection of 18.11. So I'm going to use those values when I create this sketch here. So again, right plane, I'm going to call this speaker shot. And then I'm going to make a line that is in line with this lower line. So you see that orange line stretching out there, Q for construction. I'm just going to make kind of like a flag shape like this. And then I know that these two lines are parallel. And now I'm going to use those dimensions that we saw before. So bumper is going to be 36.37. So that is the distance away based on this front structure. Now 78.13 is going to be this lower section, 78.13. And then this upper section is 82.9. Top and bottom, 82.9. And then the last one is 18.11. So this segment is 18.11. So that's going to define the speaker if your bumper's all the way up against the wall. What I'm also going to do here is I'm going to do another one. I'm pretty much going to copy that geometry again. And I'm going to make equality constraint. This is equal to this. 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 And last thing, these two are parallel. And then I'm gonna do a separate one, which is, I'm gonna say 120, and that's gonna be kind of like my far distance. This 120 was based off of like some prototyping that we had done based on like a shooter that we were working with to see like how far away were we still able to get a relatively straight shot, and anything kind of beyond this number there would be a lot of wobble in the note. So we're gonna say that this is kind of like our farthest shot that we can do. So now I have the two positions of shooting. Next is going to be the amp. Same thing, name my sketch, do it on the right side, and then I'm going to zoom in here. And the amp shape, if you look at the amp station, okay, it's an opening in the side of the wall. You can't see very well, but this segment actually relates to an angled section that's pretty much 45 degrees angled down, and I'll show what it looks like in a sketch. But this is the view we need. It's going to be 26 inches tall, and the opening is 18 inches tall. And so in my sketch here, line tool, construction, starting at the floor, I'm going to go up. I'm going to create a pocket, and then it's actually a 45-degree slant. This point is going to be vertically constrained to this point since they're on the same face. This section here is 45 degrees. This section here was 26. And then this section here was 18. Okay, and the last thing that I would need to dimension here is this opening here. If you look at the kind of wood version of this, they use a 2x4 to kind of create this section, and a 2x4 is generally 3.5 inches wide. So I'm going to use that as kind of like a reference. The depth you can get from more detailed drawings, but I'm going to use this for my main sketch just because it's close enough to what I need it to be to look at the geometry for my amp scoring. Then last thing I'm going to do is make a tangent constraint from the front of the bumper to that, because to score on the amp I'd want to be bumpers of all the weight against the wall to make it easier for the driver. And then that's my amp and my scoring stuff. So I have all of my game rules and scoring elements all in one sketch. Now it's time to actually do some sketching for the mechanisms. Okay, so first mechanism we're going to do is we're going to do the intake. And so I'm going to create a new sketch. This is going to be intake. It's going to be in the right plane. When I do that, I'm actually pressing N because I'm looking normal to the paper here, or to the page. Some of this information is going to be based on like prototyping stuff. So it's like the numbers that I'm using are based on like previous prototyping efforts, and this is what you do with your team. You'd figure out dimensions based on your prototypes and bring that into your sketch. But for now, what we're going to do is I'm going to have intake wheels here and here. I'm going to say that these wheels are a diameter of 2 inches here and here. So these are going to be like my two main intake wheels, and they're kind of floating in space here, which is fine. I'm going to define this wheel to have a gap with the floor of 1/4 inch. And right now it's yelling at me because it has a horizontal constraint somewhere. So at some point it locked into a horizontal constraint. So you could just remove that and it should move just fine. Next is I want there to be a little bit of pass-through height for the note. So from prototyping, we've seen that like if the note hits this front wheel, it kind of squishes it a little too much. So it makes the compression a lot more aggressive. And so the note, actually, the motor has to work a lot harder if this is less than 2 inches. So I'm gonna make that 2.2 to give it a little bit of room for the note to pass through without actually hitting. And then here, I'm going to use a distance of 1.9, so it's going to have a little bit of compression against the wheel. Once it gets up into the intake, there's going to be some compression on the wheel on the note between the rollers here. Something I want to define as well is I don't want this wheel to be too close to the bumper here, so I'm going to give that a 0.25 inch distance so that we know that with my 2-inch wheel here, it's not going to be projecting in front of the bumper. So that's going to actually lock in my wheel dimensions here for my intake, and I'm going to leave it there for now. We'll do the rest of the definitions for like motor dimensions and subsequent rollers. What's really important with the intake is like how the interaction of the floor goes. Okay. Next, I'm going to do a shooter. It's going to be a shooter here. Same thing, it's going to be on the right plane. And then I'm going to do 2 circles, boom, boom. And then I'm going to draw a line pretty much between them like this. I'm going to assume that from prototyping, they've told me that a 3-inch diameter wheel works well in this kind of vertical configuration, and I'm going to lock it in for both. They're both equal. And then same thing, compression-wise, dimension wheel to wheel. It's going to be 1.9. And so this is kind of dictating the spacing of my wheels. Now, they're still free to kind of move, which is fine. What I'm going to do is I'm going to go a center line from here. So looking at the center of these 2 wheels gives me that square, still a construction line. I'm going to go to the center of the speaker here. I'm going to make this a perpendicular constraint so that this line is always normal facing to the center of that speaker. So that's going to kind of define, I can move this still, but now it's constrained to always be aiming at the center of the speaker. And then what I'm going to do is I'm going to start giving it a little bit of shape here. I'm actually going to go with a pretty low shooter. So it's going to be, I'm going to assume that I'm going to design a robot that has a very limited motion, can still shoot close shot and far shot, but is designed to be very short. So I'm going to bring this in. I'm going to bring in another line that's going to go towards the intake. I'm going to make it, and these are kind of arbitrary points here, but I'm going to make it vertical to the end of this tube. And then I want this to be perpendicular. So bring that up. Okay. And let's say that like I know this is a mounting tube. My battery is over here. Instead of having it so far out of the edge over there, I'm going to remove this vertical constraint. I have this as a perpendicular constraint because I'm going to use this line as a reference of where I build the set of rollers that feed into my shooter. I'm going to do kind of like just the bottom part of like they call it the chair bot for this year, but it's like a low pivoting shooter where it rotates its arm around this location here. I'm probably going to design the pivot point of that arm to be somewhere in this location here. So I'm going to give myself, like, let's say in this, I'm going to make an L here. This is going to be perpendicular. Whatever plate I designed to hold that axle, I'm going to reference this back edge here. I want that to be vertical. So I'm going to use probably about 5 holes here to get this location. I know there's some electronics back here, so I want this arm pivot to be a bit higher. And then also something to note is what type of chain and sprocket system I'm going to use there. So I'm going to actually just look for, I think one of the sprockets we have in the shop is a 60 tooth 35 sprocket. So I'm going to look for the sketch of that 60 tooth PDF. So for a 60 tooth sprocket, the outer diameter is about 3.38. It's about 3.5 when it comes to the chain as well. So to give me a little bit of room, I'm going to create a circle here. That's going to be, what was that value? It was, sorry, 7.6. 7.6. Okie dokie. So knowing that I have some electronics up here, I want to give this a little bit of space. So I'm going to give that about 2 inches of space there. Cool. So now the last thing to define here is how much runway I want to give here. I really only want enough space so that the note can sit pretty much completely inside the robot without hanging out. That way it's not in danger of getting knocked out of the robot while I'm driving around. The note's about 14 inches. So let's say from this point to this point, we want it to be just a little bit more than 14 inches. So let's do 18. So the note will fit fully inside here as we go from different shooting positions. That's kind of, if you look at this, that's kind of really stubby. It would be really hard to start to fit all the other components in here. I'm gonna give myself a little more room. Let's make this. Yeah, let's go ahead and make that 25. That seems okay. Or 22. That seems okay. And then I'm going to also include a second set of this same line feature. So I'm going to just draw it kind of out here. Circle first, boom, boom, line between them, and then center point line to the center here. Using the equal constraint, this is equal to that. Bottom wheel equal to bottom wheel. Center line equal to center line. These are perpendicular. The straight segment is also equal. So if I were to take this and I rotate it up, it'll fall completely in line with that other section. And then from here, I'm going to go to the center of the far shot. Boom. Same thing, perpendicular. Boom. Boom. Oops, sorry, not perpendicular, parallel. No, perpendicular to the shooter face. There we go. Okay. So now this will indicate the pivot of the arm, or yeah, the mini arm that's going on here. So this is just for reference, but in order to shoot from my close shot to my far shot, the arm has to rotate just about 26 degrees. Boom, boom. So now I have kind of a general architecture of my robot. It's going to have an intake down here. It's going to have some sort of arm situation over here. And then it's going to have an under the bumper intake, pivoting shooter. We're going to forego doing the amp for now, just so we can get to designing some parts. Also, within your top level assembly, make sure you name your Part Studio segment. So this is just going to be my main sketch. And then this is going to be my top level assembly. So I have my top level assembly, I have my main sketch, and let's keep going. So I have my top level assembly. Next, I'm going to create another file. This is going to be 24A, and this is going to be my drive. Now in order to do this, I'm going to actually utilize the fact that this was a kit of parts drive that already has an assembly built out for it. Just like you would if you were to pick the normal kit of parts drive dimensions, you can just go to the AndyMark website and download the step file and import it. We're going to do pretty much the same thing, except for since the drivetrain is modified to be super small, I've created that assembly already for you. From here, we're going to actually just insert in the assembly section. Insert other documents. We're going to navigate to the same document, mentor training 24, tube and gusset structures drive. Yeah, tube and gusset drive. And then we're going to input the drive assembly. And then what I'm going to do here too is I'm actually going to remove this upper assembly. Just so we have this part of the drive ready to go. And then I'm going to create a new version of that. So now it's updating to only have this upper structure. And then once it's in here, I'm going to fix this in place so it doesn't move, and then I'm going to update it. so that it removes that upper structure. Cool. So now it just has that upper structure. Next, I'm gonna use a trick called edit in context or design in context. So in the tool search here in the assembly, I'm gonna do in context, and it's gonna show me a part studio, creating a part studio in context. It's asking for an origin, which I'm just gonna pick the origin of the assembly. Okie dokie. And it's gonna create this new part studio that has the assembly kind of shadowed behind it, so I can use the parts of the assembly as reference. So in my drive, I'm going to work on that intake structure, which is going to come off of this front side. So what I'm going to do first of all is I'm going to derive. Oh, before I do that, I have to here. I'm going to create a version of this Mainsketch. Without creating the version, you're not going to be able to derive it. So you have to create the version first. And then in my drive, I can go to other documents, navigate to my folder. And then now I have my TLA here. I'm going to want to bring in my bumper and intake extension. Okie dokie. Cool. So now that's in there, I can go ahead and create. I'm going to use this face of the tube as my sketching face, because the tube that I'm going to extend out is going to be it's going to be in line with the face of this tube. So I got my new sketch, and then I'm going to create a rectangle that goes. I'm going to just drop it in kind of in a spot. That way I can define exactly where it's going to hit. So I'm going to use my coincident constraint and go this corner to this corner, and then this corner to this corner here. And so now that's defined. I can go ahead and extrude. It's going in the opposite way that I want. So boom, 1 inch is good. So it's going to be a 2x1 going forward. Boom. That's 2 inches. That's 1 inch. Okay, that's good. Next, I'm going to use this face, sketch, and actually, yeah, that's fine. From here, I'm going to use this face, and then I'm going to make another rectangle that's constrained here and here. So since I locked it to be touching both this upper line and lower line, I know for a fact this edge has to be 2 inches. So the only thing I have to define here is this edge. It's going to be 1 inch. Okay, and then when I extrude it, it's going to be a new extrusion. I don't want it to be the same tube as this. I'm going to make it as far. It's going to be up to face, and then I have to select which face it's going to be up to. So because I also know I would have the same tube coming out in the same kind of cross section as this guy over here, I know this tube has to meet this inside face. So that's how I can create this tube without even having to dimension how far it's going to go. Okay, and this tube ends up being 2.5 inches. Okay, because it's 2.5 inches, I'm going to show you something with the tube converter. So tube converter, if I select both of these holes or both of these tubes, it'll create the tube converter section, but this hole is going to be very close to this hole, because what it's doing is it's going to center the tube and create holes symmetric from the center, which means that like with that 0.5 spacing, it's cutting the end of the 0.5 spacing in half. So this is actually a 1/4 inch spacing at the start, which I don't want. So I'm actually going to remove part 2 here so that that tube is not being tube converted yet. I'm going to create a second one. And this time when I create the second one, I'm going to ask it to go from an end. And then I'm going to select the outer face. And so it's going to start by going 1/2 inch from this outer face to create the first hole, which will also, because it's still in increments of 0.5, it's a, what was that, 22.5 inch. This also is a 1/2 inch from this edge here. So if I go to center distance here, 0.515, that's interesting. Center 0.515. 0.5. Let's confirm that again. Boom. Boom. Okay, 0.5. Yeah, I must have selected this back one over here, which will kind of bring that distance down and into the thickness of the tube, which will get me kind of a weird dimension. So I went from back here to up here, and that's what got me that weird center distance, is because it's going from like this plane to this plane, so that's going to add a little bit to my distance calculation. All right, so that's going to be the structure for the outside. Next, we're going to go ahead and design a gusset to connect all this stuff together. So the first gusset I'm going to design is going to be off of this face. I'm going to sketch, and then I'm going to create a hole pattern starting from right here and right here. So I'm going to make those two equal. This one didn't catch this the circle here, so I'm going to do the concentric constraint, Shift O there, and then these are equal. And then I'm also going to do, I'm going to do that later. What I'm going to do next is linear pattern. I'm going to select these two holes, and then I want it to be 3 forward, so that's good. And I'm going to do 0.5 inch spacing, so ½ inch spacing, and then I also want there to be 2 rows of them. So now I have 6 holes over here, 6 holes over here. I'm going to do exterior segments here. And then I'm going to connect them all with lines. Okay, and then the next thing, before I do this line, it might need to jump over this front tube here. So I'm going to do some dimensioning here to lock in some of these other parts. I'm going to say that this guy is 0.75. So that's going to make all of the circles a little bit larger because, oh, this one is horizontal, so it pulled this guy. To make sure that all these are the same, what I'm going to do is I'm going to select all of the circles, so they're orange, and then I'm going to press E, and then all of them are going to now be this dimension. Next, I'm going to do tangent constraint here and here. Because this is constrained horizontal, when I did the tangent constraint, it moved up to make them tangent to both sides. Then tangent, tangent, okay, tangent, let's try that again, tangent, boom, okay, cool. So if I were to go straight across here, boom, boom, like that, it is actually going to be hitting that front part of the tube there. So what I'm going to do is I'm actually going to add a couple more circles here and here. Same thing, I'm going to make it equal here and here. And then I'm going to make a line that goes across. It's a horizontal line, and I'm going to give this a distance. So from the top of this plate to here, it's going to be 1/8 of an inch. So we have an 1/8 of an inch gap. And that's fine. I'm going to do a sketch fillet, and I'm going to go here in this corner. Boom, boom. Okay, not sketch fillet. Why can't I? Let's do, next I'm going to do lines going from here and here. Boom, 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 boom. Tangent, 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 tangent. Okay. And then I'm going to actually just create this gusset here. It's going to be a new part. It's going to be 1/4 inch thick. And then I'm going to use the fillet tool here to go underneath. And then it's going to be a, we'll do a 1/4 inch radius for both of those. So now it should go up and over that tube. Okay, and then finally, last gusset we'll need to do for the intake structure is sketch here. We'll do here and here. Equal constraint, boom, boom. Going to do linear pattern up. 3.5 0.5, and then linear pattern here, 0.5, go the other way. So now all of those are grabbed. I'm actually going to do an extra hole here too, just to cap a little bit more. So since I did an extra hole over here, what's actually going to do, let's actually do this the right way. So if I were to leave it like this, I decided in the moment to create this extra hole. If I were to redesign this and make it a different length, the tube converter would redo the tube conversion calculation, and then it would end up shifting all of these holes. These holes would remain in the right kind of gap from each other. This hole might migrate. So I'm actually going to remove that. I want to link all of my holes together. What I'm going to do is I'm going to delete that concentric mate. I'm going to redo the concentric mate to this back hole here, and then change this to 4. There we go. Now I can go here, here, and here. Then 0.75. Then all 3 of these equal. I'm going to do line here, and then for this corner over here, I'm going to end up doing some sort of mounting plate situation on this inner tube for the intake. And what I don't want to happen is I don't want this gusset to cross over this corner to eat up some of that space, just in case if I did a line like this, just in case if this intake tube needed to go forward a little bit more, this gusset, if it was designed like a triangle like that, might get in the way. So what I'm going to do is I'm actually going to go vertically up here and then horizontal here, and then I'm going to use A for a segment of a circle or an arc, and I'm going to drop it in just like that. Now I'm going to use tangent constraints on the outside here, lock those guys in, tangent constraint, tangent constraint, tangent. I also want these lines to be tangent to this inner arc. And then I'm actually going to give this a little bit of space. So I'm going to do 0.065, so a 1/16 of a space from the arc to the corner, that tangent in hole. There we go. Cool. So now with all of those things, I actually didn't define what this radius was. All I know is that I want it to be tangent to these 2 lines, and I want to have a 1/16 gap from this corner here to give a little space for if there's a structure somewhere in this corner. Now I'm going to do this corner gusset. We can probably get away with an 1/8 inch gusset there, so I'm going to do 1/8 inch. So that's the structure for my intake. And then when I create my assembly, I'm going to do this in kind of a fast way. So I'm going to insert. I'm going to do this entire part studio, current document now. Do this entire part studio. I'm going to take all of these sections here, and I'm actually going to group them together because these are already in the orientations that I'd want for the mating. This grouping is going to allow all this stuff to stay together, so that if I were to try to drag it, they all kind of stay together, which will just make my assemblies a little bit faster. I'm going to mate that circle to this circle here. That brings it down. Now all that's left is to make a copy of this guy, a copy of this guy, and a copy of this guy. Well, another way to do this too, instead of doing copy and remating, let's do it this other way. What I'm going to do is I'm actually going to select this, and I am going to linear pattern it going this direction. Boom. Change the direction, and I know that it was about 22.5 going to inside, and you'll see it hits right at the corner there, so that's actually going to be, in order to get all the way, it's going to be a +1. Parentheses. Since the tube is 1 inch thick, I just add 1 to that dimension, and it'll move over the thickness of that tube. There we go. Another linear pattern, this guy, same direction, 22.5. It's going a little too far, and we know that this is a 1/4 inch piece, so minus 0.25, that comes out. And the last one, this one, it's gonna have to flip. So I'm actually going to create a copy, select this corner, and if you imagine, this has to rotate all the way over to be on this corner. So the top of this gusset is going to be the bottom of the gusset on the other side. I'm gonna flip it around and rotate. So now it's in the right orientation. And then I'm gonna take these two pieces. I'm gonna do another linear pattern. I'm gonna go down in direction. Okay, and then I know this is a 2-inch tube. This is an 1/8 inch gusset, so it's actually gonna have to move down 2 plus 0.125, and that's gonna get me that distance of travel to get to be a bottom gusset line up there. So now that is my intake structure with all the gussets included. Before we move forward, I'm going to go ahead and delete this part studio because I haven't really been using that, or I'm not going to really need to use it. I'm going to move this guy up front so it matches the rest of the configuration. Rename this one 24A drive, and then this is going to be rename drive for drive assembly. Okay, so next we are going to start using the part management system. So all the drivetrain parts we already know that would come from the kit of parts. What we now would need is we would need to actually create material so that the fabrication team could fabricate this tube, this tube, this tube, this tube, and then these gussets. We'll need 2 of these long tubes. We would need 2 of these shorter front tubes. We would need 1 of this long tube, and then 4 of these gussets. So I'm gonna go to my part management system, and that's how many unique parts. So that is 1, 2, 3, 4, 5 unique parts. So I'm gonna grab in my part management system, it's gonna be under the drive section. So A, I'm gonna grab 1, Control Shift V, 2, 3, 4, 5. Okay, and then this we're gonna call the for the drivetrain. It's gonna be the side mounting rail. It's gonna be the stuff that I mount all the mechanisms to on the side of my robot. So that's gonna be the first thing we do is side mounting rail. And the next one is going to be the gusset here. So that's going to be the intake gusset. Let's do intake side gusset. Excuse me. And then we're going to do this shorter intake tube here on the side. It's going to be the, let's say the side intake structure rail. We're going to need the intake corner gusset. And with these, I don't love the fact that these have intake in the name in the drive structure. But they are the structure for the intake, so I'm going to leave it as is. If you could be a little more thoughtful in how you name things, that would typically better, because there might be some confusion when you start assembling whether things belong to the intake or to the drive. But in this case, I think it'd be fine. The last thing is the front intake structure tube. Okay, so those are my 5 parts. The side mounting rail, the side intake structure rail. Let's do rail, just to make all the naming conventions the same. So gusset, gusset, rail, rail, rail. This is going to be 2 by 1 by 1/8 aluminum, and this is going to be 1/4 inch plate aluminum I'm going to copy this guy. These are also going to have the same material, and this is going to be 1/8 aluminum. Okay, come on. Cool. For the side main rails, I need 2 of those. For the side gussets, I need 2 of those. For the side intake structure, 2 of those. Corner gussets, I need 4 of those. And then the front intake, I need 1 of those. And then again, for the fab process, it would be like, what is the most time intensive or labor intensive part? These would all be CNC parts. At least for us at UNLV, the tubes themselves, the whole pattern is going to be done by the UNLV Me shop, because they could use the larger Haas machine there. But for the flat plate gusset itself, we'll use the CNC router that's in our lab, and that would be sufficient. And then for the part files and for the drawing files, because the rails are going to be made at the UNLV Haas machine, they require a solid part file, and I'm just going to use solid part as just the text for each of these. This eventually will be a hyperlink to a part file. And then for the side intake gussets, those we're going to use DWGs. So I'm going to use that. And then for the drawing, I'm just going to use the part numbers, going to grab the text there. It's going to be a hyperlink later. So, okay, so now actually if we wanted to send this over to Fab now, the things that we would need for the UNLV shop is this would need to be a solid part file. This would need to be a DWG file so we could do it on our OMIO in the shop. And then these would be PDF drawings that we can then use to verify and inspect the part after they're made. So now I'm going to take this information. We're going to go to that drive file here. And then we're going to go to the part studio, and we're going to start to modify the properties of those parts so that we can name them. Okay, and then also this part here, because it's in the other file, the part that I derived, it's not showing up in my part studio here, which is okay. I'll actually just redo it in here so that we can utilize the part studio in the same way, because typically you wouldn't have like this structure here in the drive file, which is fine. So in my plane, I'm going to go up here. I'm going to go boom, boom. I'm going to extrude it up to this face here. Cool. And I'm going to tube converter it. So now it is a tube. There we go. So now it lives in this part studio as well. So then I can change the properties. Now in this properties, I'm just going to go to my part management system and go pretty much line to line, part name, part number. It is revision 1. And then I'm going to go to the titles here. So title 1 is the material. Title 2 is the quantity. And then title 3 is the fabrication process. And then save. Do this with the next part. So the second part was the gusset. So this part here, properties. We have new part number, part name, revision 1. Title 1 is material. Title 2 is quantity. And then title 3 is machining process. Yeah, and if you also have them memorized too, you don't have to copy and paste. You could just type it in. But I'm just showing you can do less thinking work if you do it in one area and then just like make sure that it's consistent with the other area. I'm gonna go ahead and save. Now, let's say I would have gone through and renamed all these parts, right? Next, how do we actually get the stuff we need to go to fab? So first thing is I would go to this side tube, right, that I created all the properties for, and I would create a drawing for it. We're gonna use our 2024 UNLV template. Gonna look at the right side. It's too large of a piece to go onto the drawing in 1:1 scale. If you can, if it's small enough, you try to do every drawing 1:1, but since this is too long, I'm not. All I really need is the side view and the front view, and that should, actually no, we also need the top view. And then the information that the fab team would need is they would need to know how long this tube is, what is the cross-sectional dimension, so it's a 2x1, and then the thickness of the tube is 1/8 inch. So this information here lets them know, along with the pre-populated. So the reason why we did the properties is so it pre-populates the title block here. So they already know it's a 2x1 by 1/8 aluminum tube, and they know that it has to be at least 20 inches in order to make this part. I typically like to remove the center marks here. And then I also, the other thing that the fab team would need to know is what are the size of the holes here, so that they know what size drill bit to grab. And then I wouldn't necessarily dimension all of the holes here because that those identity informations would be in the part file. And when they cam it up, they just can pick it from there. And so this is pretty much the only information I would really need in that drawing, for at least for our process with the fab team. Next from here, I would export this file as a PDF, so that's good. And then I would rename it to match this convention. It's gonna be part number dash part name. It's going to export, and then it's gonna pop into my downloads. Cool. And then I'm going to go to my structure here in Drive, and I'm going to go to my PDF drawings, and then I'm going to drop it in to my PDF drawings. So now that that's here, my PDF drawings, I can copy this link, go to my part management system, and then insert that link here. So now in the part management system, the fab team can go in here and be like, okay, what is this part? What does it look like? Jump straight into the drawing. Now for the solid part file that we need, I would right click this part again, and I would do export. Here, I want to have the format as SolidWorks, and then same convention before, it's going to be part number dash name export. Starts to download, go into my part files section here and drop that part in here. Now I can copy this link, go to my part file, insert link, apply. Okay, so now all of this line 1 is complete for the fab team to start fabrication. So this is selected not started. All these we could say they're not obsolete because these are still designs that are needing to be made. If there is a revision and the revision wasn't complete, but we know this part is going to be changed, we would change obsolete to yes until we get that revision out, so the fab team knows that they don't need to make any more of that particular type of part. But once it gets to this status where everything's filled out and fabrication is not started, obsolete is no, fab team should know that, okay, this is the part that's ready to go. And then intake gusset, this is the type of file that we need for internal use in the shop for our CNC router. So that process looks very similar. So first, I still need to create a drawing for this part. So create drawing, UNLV template. This one should be small enough to where I can use a 1:1 scale. Cool. And then what the fab team needs to know here is, how long of a piece are they going to need? How thick of a piece are they going to need? And then what size drill bit do I need for the holes? They would also need to know the width of this piece here. Let's go from this side. Boom, boom. Cool. So now they know at least the area of material they'll need to make this part. So that's pretty much all the information the fab team would need in order to get this part going. So I can export this part management system, get the part number, part name, export as PDF, come back here. I have to pick, so I'm going to export this as a DWG. I'm going to make sure that I select the face that is the defining face for this part, right? So they already know the thickness of the material. They could do the drill depth in CAM, but this face is what we need for the DWG. This is what's going to create kind of like the 2D profile for this part. So I'm going to same convention, part number dash part name, formats DWG, export that. Now I can go to my drive here. The DWG goes in the part files folder. The drawing goes into the drawing folder. And then I'm going to grab this link here. For the drawing. And then for the part file, copy the link and insert that link. Cool. So now we have an example of a part file that we can send this information to the UNLV shop to get that tube CNC cut, and then this would be an internal file that we can put on the CNC router, and all the information there for the fab team is available. So that's how we use the part management system. And then another thing I'm going to do is I'm going to take these two and put it into a new folder. I'm going to create a drawings folder inside of my part studio, or inside of my document, and then I'm going to put all of my drawings into this drawing folder. So you can keep it organized. You'll have your part studio, you'll have your assembly, and then you'll have your drawings.